The night on the moon lasts for 354 hours. That is a long time to go without power and too long for batteries to keep your equipment from freezing. With the high investment cost of developing infrastructure on the moon, operations need to take advantage of the entire moon's day and survive the long cold night. With power beaming providing enough energy to keep the station in standby, it can quickly restart operations when power levels increase as the sun rises. The moon has a few great locations where the sun shines at almost all times and is only on the north and south poles at the highest points of the craters and mountains. These locations will be highly sought after and will limit what operations you can accomplish based on rugged terrain. Being able to place a facility where the minerals are most dense or easily accessible will increase production and profit. These satellites will open up a large area of the moon along the equator for mining and industry. Why do we need to mine the moon? It comes down to cost per pound into orbit. With the space economy heating up and even with Starship becoming space-worthy, it will still be too expensive to launch large amounts of mass into orbit to create an orbital infrastructure. This problem can be solved by using the lower gravity of the moon along with the lack of atmosphere to create a launch platform that moves away from expensive rockets and toward a mass driver system. Initially, the majority of material mined on the moon will be used for building a lunar infrastructure with mines, processing stations, and manufacturing, then eventually orbital structures. The moon's mass is not evenly distributed, which disrupts low orbits and requires corrective maneuvers to maintain orbit. This is alleviated by increasing the altitude of the orbit to above 100 miles. Going to much higher orbits of around 400 miles would also create a problem of the Earth disturbing the orbit. Having an orbit of 150 miles around the equator will allow a mostly stable path needing the least amount of station keeping. 4 krypton ion thrusters will allow gentle corrections to keep the satellite in position. How much power does it take to keep a small mining operation from freezing? The moon at night can drop down to negative 200 degrees Fahrenheit and as high as 250 degrees in a day. These huge temperature swings will require everything to be built with advanced insulation materials, which adds higher costs. If we can prevent the machines and computers from having such extreme temperature swings, we can lower construction costs and extend the life cycle of the facility's equipment. The idea is to use a series of solar-powered satellites to power a laser and beam that energy to a receiver on the surface of the moon. Currently, we will be restricted to a 10 kilowatt laser because of weight and size limit, and with the low efficiency, each receiver will collect 1 to 2 kilowatts of continuous power. With 16 satellite power stations evenly spaced at 150-mile altitude and 1 ground facility on the surface of the moon, the receiver would be able to have up to 4 simultaneous beams providing up to 2,200 watts of continuous energy. These satellites will need a large set of radiators to keep the laser and other systems cool. A 10 kilowatt laser will need around 20 kilowatts of heat dissipated. This will be accomplished with both a forced convection and latent heat transfer. The receiver is a series of photovoltaic cells tuned for the laser wavelength. Each facility will have solar panels to provide the main power during the daylight. The orbital period for the power satellites at an altitude of 150 miles and at a speed of 3,521 miles per hour will take 132 minutes per orbit. Each orbital pass will place the satellite in the shadow of the moon for 37 minutes. This will give 95 minutes of sunlight to charge onboard batteries and capacitors for the night side. The satellite is designed to keep its orientation and only use onboard ion thrusters intermittently for station keeping. The laser will be mounted with 3 reliable stepper motors that will aim the laser at its target. The constellation will also act as a global positioning system for the moon to provide an accurate coordinate system aiming the laser. These satellites would be a first-generation power beaming system. As beam divergence is reduced and larger power and smaller units are available, the possibilities are endless. With Starship, we could eventually have thousands of satellites with an orbital spread similar to SpaceX Starlink constellation. This could eventually provide enough power to keep a facility continuously running at full capacity anywhere on the moon.